Hello everyone, our project title is 3D reconstruction from multiple 2D images. The team members are myself Abhishek, Vijay, Vishal and Yashas. So what is 3D reconstruction? It is the creation of three-dimensional models from a set of 2D images. An image does not give us enough information to reconstruct a 3D scene. This is because during the image capturing process, a three-dimensional scene is projected onto a two-dimensional image. So during this process, the depth is lost. So the goal is to infer the 3D geometry and structure of objects and scenes from one or more multiple 2D images. 3D reconstruction using LiDAR is expensive and is prone to artifacts from GPS and IMU sensors. Hence, we are using structure from motion algorithm as it does not require any expensive setup and we can simultaneously obtain the camera poses of the monocular camera with respect to the given scene. Some of the applications where 3D reconstruction is used are in medicine, augmented reality, city planning, gaming, etc.
The recent progress in the field of 3D reconstruction are the major bottlenecks of the SFM pipeline are the feature matching and the bundle adjustment. Hence, the paper tries to address the problem of feature matching by proposing an efficient process to match all the pairs of images in a database without any need for an exhaustive test between each image pair. The method uses a visual vocabulary which can store 16 million visual words, and this vocabulary has two layers. The features are extracted from the images and are converted into shift descriptors, which are then used to generate an inverted file. This inverted file is used to form clusters of the images from which the image pairs of all the pairwise matches are obtained. These are passed to the bundler, which returns the sparse 3D reconstruction of the scene. The major drawback of this method is that it is stricter than the conventional method of feature extraction, hence making it unable to find the complete tracks for an object point, hence leading to a longer time for the 3D reconstruction of the scene using the bundler. The point clouds generated are usually noisier, which causes the correspondences detected by this method to be not very accurate. The usual time complexity of the SFM pipeline is of the order of n power 4 for n images. The paper thus aims to improve the time complexity to order of n by proposing a preemptive feature matching technique and a preconditioned conjugated gradient bundle adjustment. The retriangulation step is also introduced into the pipeline, which deals with the problem of accumulated drifts without an explicit loop closing, without sacrificing the time complexity of the method. The preemptive feature matching technique decreases the pairs of image matching by up to 95% while still recovering good matches for the reconstruction process. And the bundle adjustment process uses a Hessian matrix instead of the Square complement. The major drawback of this method is that it might fail for extremely large reconstruction due to the high accumulated errors, and also the number of image pairs matched to test for the SFM pipeline is of the order of n square, which is higher than the vocabulary strategy, which has an order of n.
Before we work on SFM, we must map the association between all the images. This is done using three steps: feature extraction, feature matching, and geometric verification. Feature extraction can be done using any algorithm like SIFT or ORP. Feature matching involves calculating the associativity between the features and among all the image pairs. The resulting association will contain a lot of outliers which are then removed using an essential matrix in the geometric verification phase.
So after performing the data association, we take two non-panoramic views and compute the 3D points. Linear triangulation algorithm is used to obtain the 3D points. The next step is to add a new view into the system and calculate the 2D correspondences among the views and use that to compute the 2D to 3D correspondences. Thus, we incrementally add new views to the system and calculate the 2D to 3D correspondences. Once we have established all the correspondences, we will use the PNP algorithm for computing the camera poses. Then the bundle adjustment algorithm is applied on this to refine the camera matrix and the 3D point. We can now use the camera matrix and the 3D points that we just calculated and construct a 3D model, and this 3D model can be viewed in Mesh Lab.
Hello, I'm Yashas. I'll be giving the demo of the code. The code is split into two parts: the image loader class, which handles all of the image imports and the downscaling functions, and the SFM class, which has all the helper function needed to run the structure for motion code. To run the code, simply initialize an SFM object with the directory of the image dataset as an argument and call the object. On running sfm.py, two windows open up. The window on the right shows the reprojection error, while the window on the left shows the image which is currently being projected. The code writes two files: a .ply file which can be opened in a software called Mesh Lab, and a CSV file which stores all the pose arrays. The Gustav model in Mesh Lab, SFM has mapped it quite well. The changes in height, depth, pose, etc. are clearly mapped very well. You can also see the lamppost which appeared partially in the dataset has also been mapped. We can utilize the bundle adjustment by setting the enable bundle adjustment argument to true while calling the SFM. Bundle adjustment enhances the model extremely well. It takes a very long time to run. It takes around 10 minutes to run on a dataset of 8 images. You can see that the bundle adjusted model is almost free of outliers, and the depth and height estimation are very accurate compared to the actual image.